Welcome back, guys, and I do hope you and your family are well. So, what we're going to look at today is the radiation of heat. So, let's have a little bit of a recap. You've done some work now on how heat transfers through materials, and we've looked at the conduction of heat, and heat conducts really well through metals, which are solid, and not really at all well through gases because the particles are too far apart to conduct the vibrations through the heat, and also they don't have free electrons which can move. You've looked at convection. Now, convection can't happen through a solid because if you remember, convection happens in fluids where they get heated, expand, become less dense and rise. So you can get convection in a fluid, that's a liquid or a gas, but you can't transfer heat via convection in a solid. So the last one I wanted to look at was heat radiation. Now, those of you who are a little bit more thoughtful about what we've done might say, but FJ, we get heat from the sun. When we're lucky enough to be outside, we can lie on the beach and feel the heat from the sun on us. And we know it's there even when we close our eyes. We can't see the heat, but we feel it. And I'll go, yeah, what's your point? Well, the point you're trying to make is that heat has got through space. It's come from the sun, and it's gone through a vacuum of space before it's hit the Earth's atmosphere. So just outside the Earth's atmosphere is a huge distance to the sun, and there's nothing out there. There are no particles, so there's no solid, no liquid, and no gas. So if there's a vacuum, no material at all, just emptiness, then there's no particles to vibrate and free electrons to conduct. There's no material to convect, so there must be another way that the heat gets to us from the sun. And that method is called heat radiation. Conduction, convection, and radiation. A lot of teachers start with radiation first. So that's why I'm sitting in this corner, because here's my radiator, and it's actually lovely and warm at the moment. What's interesting is, if I hold my hands in front of it here, I can feel heat coming off it. Well, it can't be heat due to convection. It can't really conduct through the low density air. So this must be heat getting to us in the same way that it does through the vacuum of space. And this is radiated heat coming off the radiator, hence the name, of course. So how does that work? Well, it's really quite simple. The sun gives out light, and you know about the colours of the rainbow, but it also gives out other waves. Light's a wave, and it gives out other waves in the electromagnetic spectrum. And one of them is the one that you see when you put night vision goggles on. You must have seen those films on YouTube and on television of police chases and the pilots in the helicopter chasing the person who's robbed someone or whatever they've been up to no good. They can see them even in pitch dark because they have a special camera that turns their body heat, the radiated heat from their body, into visible light that the screen in the helicopter can see. So there's invisible light coming off this radiator. And it's not light that humans can see. I believe some animals, I think it's snakes and things, can sort of sense it and pick out a sort of picture of what's in front of them. But what we do is we can close our eyes and we can feel those waves coming towards us. Now, light waves are high frequency waves. Blue is very high frequency, green is a lower frequency, and red is even lower. And if you go lower, below red, you get to infrared. And there we go. That's what radiated heat is. Radiated heat is infrared waves being given off by a hot object. Now, we know that, so let's see if we can take it a little bit further. What would happen if I put a mirror in front of the radiator? Well, firstly, you'd say it's obvious you wouldn't feel the heat because the mirror's in the way. Yeah, that's true. That, of course, is true. But a mirror is shiny and it reflects light waves. So I wonder if it would reflect infrared. And indeed it does. So I haven't got it set up like this in my lab, which is a bit of a nuisance. This radiator is currently heating the back wall a little bit. And it would be nice if the heat that came off the back of the radiator came towards me. So if I put a shiny surface behind here, maybe some kitchen foil or something like that, the radiated infrared heat waves would hit that and reflect off and come back to warm me up. So I'm going to move the camera in a minute, and I want to show you a couple of examples of where we can demonstrate the reflection of infrared waves. But at this stage, you might just want to pause the video and think, do I now understand how radiation works? Do I understand it's the way heat can go through nothing? It can go through a vacuum, and it's carried by invisible infrared light waves. So I've just been into one of my cupboards to grab a piece of kit, and I'll just open it up to show you. So this container has got a really shiny inside. It's kind of a really big thermos flask, or vacuum flask they call it in the exam. And I'll tell you a little bit more about what it really is used for in a minute. But could you imagine that I put a hot drink in here? If I put a hot drink in here, the inside surface is really shiny, so any infrared heat that goes outwards hits the shiny surface and reflects back in. So, if that's the case, it keeps my liquid really warm. In fact, this is used for something completely different. It's called a Dewar flask, invented by James Dewar, who was actually an old boy of school I used to teach up in Scotland. And James Dewar was trying to liquefy air, so he wanted the air to be very, very, very cold. So he invented this kind of flask, and it has lots of good design features. But the main one is that if you put a really, really cold liquid in here, so liquefied air, well below 0 degrees C, then you don't want heat to get in. You don't want heat to get in and turn that liquid air into a gas at room temperature. So the container in here is silver all over, both on its inside layer and on its outside one. So any infrared heat trying to get in to warm up the liquid air will reflect off the surface and leave the container cold. So it's an absolutely brilliant device. It's worth pointing out, by the way, that means that a thermos flask, or a vacuum flask, as they call it in the exam, can be used on the beach to put a warm drink in, because it doesn't let heat out. But why not fill it with ice cream or ice cubes? Because it doesn't let heat in either. So I've come into the Echo-E prep room, but there was a piece of apparatus set up in here, and so I thought I'd just quickly show you that. I'm sorry I haven't got time with all the lessons we're having to make for everyone in the school who's now at home to get this up and running, but I'll just talk you through it very quickly, and maybe when things sort themselves out again, I can actually do it properly as at FJ's Physics YouTube. I've got a curved reflector here. Have a think of that. It's like a satellite dish at home. And this is a radiant heater. So if I was to turn the heater on, you wouldn't see any heat coming off it. You can't see heat. It's infrared. You'd see it with night vision goggles. And the heat goes in all directions, but some of the heat hits this dish. And this dish produces a focused beam of infrared waves. Remember, infrared is like light. I mean, it's not dissimilar to radio and microwaves if we can use a dish. So that focused beam of infrared heat hits this dish, bends inwards to a focal point here. And what we usually do is put a match at that point. And if you take the dish away and turn on the heater, that match will sit there forever. You can put your hand here. But if you have a dish behind the heat source, this infrared beam will focus down to here, or it's probably about there actually, the focal point of the dish, and there will be really, really hot. And give it a moment or two, it's probably a minute or so, and there'll be enough heat there to cause that match to spontaneously ignite. Some of you might have heard the story about, I think it was the building in London, was it the walkie-talkie building? I'm not sure, that was curved in a dish sort of shape. And on a really sunny day, like it is in here at the moment, those rays hit the building, reflected off it, so that's the infrared reflecting off the building, came to a focal point and actually burnt the paint on cars that were parked outside. So it's an important thing to take into account when you're an architect. Great, so I hope you're a bit better now at understanding how heat transfers. Do have a look at the videos again and check that you fully understand conduction, convection and radiation, and maybe learn the Thermos Flask and its features. Anyway, I'll be making another video lesson soon, and I look forward to seeing you then.